All right, welcome to our last 12-12 lab this semester here in North Georgia. We're going to be taking a look at the electrochemistry lab this week. And so this lab, relatively short in terms of actually doing the experiment. Calculations might take a little bit longer, just to kind of get a feel for what you're doing with some of this if you haven't got a chance to do it in lecture just yet. But really when we talk about the idea of electrochemistry, what our focus is going to be on is really on electron movement. And so mainly what we're going to be looking at is what we call redox reactions. Oxidation reduction reactions where there's electrons that are going to be transferred during that reaction. And these reactions are really useful because we have a lot of ways to control them, and they're very kind of predictable in terms of the amount of energy we can get from them to actually do things. So if you think about like electricity or batteries in particular, is probably one of the best examples of using electrochemistry, but there's a lot of applications of electrochemistry in terms of being able to actually do work or being able to kind of like achieve something with a chemical reaction that's taking place. Now, what we're going to be focusing on in this lab in particular, we're going to be taking a look at galvanic cells and kind of measuring cell potentials for galvanic cells and using that to kind of find other information for one of our parts of our experiment. We'll take a look at using it to find KSP, for instance. Now, what a galvanic cell actually is. So galvanic cells, typically there's going to be two halves. In our lab, they're actually all kind of be in one component, and we'll kind of see a picture of that as well. But kind of generically, your galvanic cell usually has two main halves. You're going to have one half that gets referred to as the cathode, and this is where you're going to have a reduction reaction occurring. And you'll have another half of your redox reaction, basically where you're having your oxidation. That's going to be called our anode, making up the other half of our galvanic cell. And so we see here on the left half of the cell that's imaged here, we have a copper strip of wire, and in solution we have copper 2 plus in the solution. And what's happening is this copper 2 plus is using two electrons that are actually going to be coming from the other half of the cell to basically get reduced into copper metal, and now it's kind of depositing itself onto this copper strip of wire. On the other half of our cell, we have a zinc strip of metal, and what's happening over here, we're getting oxidation where the zinc is actually getting oxidized to zinc 2 plus, and as that happens, zinc 2 plus gets released into the solution, and we now have electrons that are now released, and basically those electrons, if we connect our two metal strips, those electrons can travel now across the cell. And the last main kind of feature of all galvanic cells, to try and keep them kind of flowing properly, is this idea of what we call a salt bridge. And so in this case, we have a salt bridge here that has our sodium sulfate in it. And really this is just to provide counterions to prevent charge buildup in our cell. Because if our electrons are constantly traveling from right to left in this particular image, the left half over here where we're getting our reduction, eventually this is going to build up a pretty big negative charge compared to where it started. And on the right side where we have our oxidation right now, then it's going to build up a pretty big positive charge as it continues to oxidize the zinc. And if we have a bunch of positive charge over on the right and a bunch of negative charge on the left, well, these negatively charged electrons are going to have a hard time continuing to move from right to left in the cell. And so, because the negative charges over here will repel each other. And so what this salt bridge does is it has just ions in the solution, so that now if we have a buildup over here of negative charge on the left side, we have sodium ions that can come over here and balance that negative charge. And we have sulfate ions that can go to the right side of our cell and balance the positive charge that's building up over there. And it just keeps the charge balance in place so that our electrons will just kind of continue to flow and the redox reaction will just kind of continuously happen without really slowing down. Without the salt bridge, your redox reaction would start taking place, but it would probably very quickly start to slow down, and eventually it would just stop, and you would start to lose your flow of electrons from one side to the other, and now your cell isn't able to really do work anymore. Now you're kind of like losing the actual purpose of that cell. All right, now, some notation with galvanic cells. So this is again kind of for that cell that was imaged on that last slide. Here we're seeing we have zinc metal going to zinc 2 plus and 2 electrons. That's our anode reaction, it's the oxidation. And you always know it's an oxidation because electrons are on the product side of it. Here we have our reduction reaction that was taking place in the cathode portion of our cell. So we have our copper 2 plus 2 electrons making copper solid. Putting all this together gives us our overall reaction. And this shorthand notation you'll see for a lot of galvanic cells is always going to start with the anode half of the cell, and it's always going to start with the solid in that anode half. And if I back up to that previous image for just a second, you'll notice there's these metal strips. There is always going to be a metal strip of some kind, even if the metal strip itself is not part of the reduction or oxidation reaction occurring. There's always going to be that kind of metal surface for an oxidation or reduction to take place. We call those our electrodes. And so in our case, for our experiment this week, we'll have a copper electrode and a silver electrode as our two electrodes. It'll actually be a silver chloride electrode. And we'll kind of get to that with our own experimental setup in a little bit. But notation-wise, here's our solid electrode for the anode side. So we actually refer to this solid. This is the anode, the zinc solid here. We have this single vertical line that represents a phase change going from zinc solid to zinc 2 plus in the aqueous phase. Then we have this double line here, which kind of separates the two halves of our cell. It also can think of it as representing the salt bridge. And then on the right side, we have our cathode. Right? And so here we always want to start with the anode on the far left and end with the actual cathode on the far right. So again, the solid on the far right. And so here we have then again a phase boundary with the copper 2+ going to copper solid. And so in general, you're always starting off solid on the left, and that's where your oxidation is taking place in your anode. And then you have kind of your redox reaction over here and your different components separated by a phase, whatever phase differences there might be. And then on the right half of the notation, you're always going to have what's happening in the cathode. It's your reduction reaction, and you're always going to end with the solid on the far right. And again, you have a phase boundary that'll just show up anytime you have a difference in phases between things. Now, when we talk about this idea of cell potentials, so when we're trying to figure out, for instance, like how much energy or things can we actually get out of our cell, like if we want it to actually be able to do work, a lot of times what we'll measure is what we call a cell potential. We use a unit of volts to actually measure that. And the way we typically calculate cell potential is simply by taking the standard reduction potential of the cathode minus the standard reduction potential of the reaction happening in the anode. And how this is going to work, standard reduction potentials, these are known values for a lot of different kind of common oxidation and reduction reactions that are all compared to the reduction of hydrogen. So for the reduction of hydrogen, we have 2H plus 2 electrons is making hydrogen gas. We say that this is kind of the standard reaction that has a standard reduction potential of 0 volts, so just equal to 0. And so the actual reduction potential for some other reaction then tells us, is it going to be easier to reduce or harder to reduce than hydrogen? A positive reduction potential, so like this E naught red, if that value is positive, that means that's something that wants to get reduced. It's easier to reduce than hydrogen. If we have a negative reduction potential for something, that actually means that it's harder to reduce than hydrogen. And typically that means that that thing would rather be oxidized instead of reduced. Because when you look at tables, and for using kind of this equation as far as like how it generally works, I'm going to just put up a table of standard reduction potential values. So we have a bunch of different reactions here. We have standard reduction potential values and voltages over here on the right. And if we think about the example that we had shown before, it had copper 2+ and zinc in it, right? So here's the copper reaction. Here's the zinc reaction. And here we see copper 2+ plus 2 electrons going to copper. That's a reduction reaction. Its reduction potential is 0.34 volts. For zinc right here, we have zinc 2+ plus 2 electrons going to zinc metal is negative 0.76 volts. Since the copper reaction has a higher reduction potential, this one wants to get reduced. The zinc, since it has a lower reduction potential, actually wants to go in reverse and get oxidized instead. So the zinc's actually going to get oxidized and go backwards. And so that's why when we actually go to calculate the cell potential, if we're looking at this equation, it's the reduction potential of the cathode, which is your reduction reaction, minus the reduction potential of the anode. And so in that case of like that copper and zinc cell, we'd have like 0.34 volts minus a negative 0.76 is going to give us a positive like 1.10 volts for the whole cell potential. And what you should see for galvanic cells, your cell potential should always be positive. Should be the general thing that you're kind of observing out of them. Because these galvanic cells, their main purpose is to really just be a spontaneous redox reaction that's going to always give us kind of this positive voltage. It's going to give us this flow of electrons out of that reaction. Like we don't have to do anything special to the reaction itself. Pretty much just have to connect it all and just let it react spontaneously. All right, now the last part of the lab, kind of calculation-wise for this week, will involve something called the Nernst Equation. And this involves looking at things that are not at standard conditions. Since most galvanic cells are going to be using solutions, they are kind of limited in terms of being able to calculate these standard cell potentials, because we can't always just use a standard cell potential if we're not at standard conditions, right? So standard conditions, when we see that little degree symbol, means 25 degrees Celsius, means that we're at 1 atmosphere of pressure. But the big thing is for solutions, it means all solutions have to have a concentration of 1 molar, which is just not very realistic. And so we need another way to kind of talk about cell potential for any situation. And that's really what the Nernst equation gives us, is a way to look at cell potential basically under any conditions if we know our temperature and we know our reaction quotient. Turns out, though, for most electrochem things, we're going to be at room temperature, 25 degrees Celsius. So this temperature part here, R and F are also constants. We can take R, T, and F if we're at 25 degrees and simplify it all into one constant. We do actually switch from natural log to log base 10 here. But we can actually then use this equation to relate cell potential versus standard cell potential at any particular point in time, as long as we're at 25 degrees Celsius. And so the standard cell potential here This can be calculated with just kind of like that, reduction potential of the cathode minus reduction potential of the anode that we saw previously. The N that we see in this equation, the only other variables besides the actual cell potentials are going to be the N and the Q. V is just the unit here, it's volts. This N is going to be just the number of moles being transferred, number of moles of electrons being transferred in your balanced redox reaction. And then Q, when you see it in this equation, it's just the same capital Q we've seen other times this semester. It's going to be our reaction quotient. So this is kind of tied back then to equilibrium a little bit. And so you can actually kind of look at, based on where your reaction is, what should have happened to your cell potential compared to what its standard cell potential would be. All right. And what you'll be doing kind of in the lab for your two different parts, first part of the experiment, you're going to be, both times we're going to be measuring this part, just the actual cell potential. And in part one, we'll be using that to find the standard cell potential and actually look at kind of comparing the standard reduction potential of copper 2+ to the known values. Then you can actually see from our table that we saw a slide or two ago. In the second part of the experiment, we'll actually be trying to find Q out of this equation. So we're going to measure C cell. We can actually calculate the standard cell potential. We're going to solve for Q, and we'll use this Q to actually find KSP for copper sulfide, as what the second part of the experiment is going to do. Now, the actual experiment itself, I kind of already mentioned, these are kind of our two goals, like finding the standard reduction potential of copper 2+ and eventually finding KSP for copper sulfide. But for the setup, a couple kind of quick things here on the setup. Our cell is going to be a little bit different. Instead of having like two different halves or kind of beakers with solutions, all of ours is going to be in one container. So that's a little bit different than maybe the most galvanic cells you're going to see. But we are still going to have kind of two metal strips. We're going to have the silver chloride electrode here that's going to be going, and I'll go into more detail on what's going on over here in a second. We're also going to have a copper wire as our other electrode. And what we should see is that your copper wire and the tip of your kind of glass, this is going to be a glass tube when you see it for your setup, should actually end up going into the solution that you put into your kind of cylinder. Now, for the silver wire, this setup with the glass tube is actually probably where 90% of your time is going to be spent in this lab. And what you're going to want to do is you're going to get a little tiny piece of cotton, and you're going to put it in this glass tube. And the glass tube is actually already pre-stuck in the stopper. You actually probably don't want to take the glass tube out of the stopper, leave it in the stopper. So you have the stopper in this glass tube, take this little tiny piece of cotton and put it in the bottom, and you want that cotton to be pretty much as small as possible and still stay in the bottom of that tube. And if you have to ask the question, is this too big? It's probably too big, and you should probably make it a lot smaller. It should really be just barely enough to kind of take up and plug up the bottom where it's not falling through. And the reason we want it to be relatively small is if it's too big, we're not going to have an actual kind of salt bridge be able to be formed here. We're going to be using something called agar. And this is the actual kind of really, like I said, the longest part of the setup of this experiment is what you're going to do is you're going to take, once you have this cotton ball at the bottom of this glass tube, you're going to take this tip and you're going to dip it down, and it's like it's almost going to look like a gel, but it's a solution of hot agar that when you pull it out of that solution, that agar will quickly solidify. But what you want to happen is that liquid agar, when it's in kind of the gel-like state, it should, when you put the tip of your tube into it, the agar should come up above the cotton ball. That is the goal. You want the cotton ball to be basically completely surrounded by the agar in that solution. And now this serves as kind of a plug so the silver wire won't fall out the bottom of your glass tube. But it also serves as a salt bridge, because the agar, what it'll allow to happen is your ions can still kind of pass through from the solution on top here to the bottom if necessary, but your actual wire or other things are actually not going to be able to do that. And so it serves as kind of our salt bridge to kind of connect our pieces in this particular case for our reaction. Now, the other parts of this, at the top, when you put your silver wire in, we need some of the silver wire to actually be above the actual glass tube itself, because we need to be able to clamp it with a clip for measuring the voltage. And so leave a little bit of this silver wire above and use parafilm, and your lab instructor can demonstrate how to do this. We have lots of parafilm. Parafilm is kind of like, it's almost like sticky wax paper that stretches a lot. And you can just take the parafilm and just kind of wrap around the top up here so that you can actually kind of hold the wire in place. And that way you just need to make sure the silver wire is actually down submerged in the KCl solution that you're going to add to this glass tube. So you add a little bit of this KCl solution to your glass tube, get the silver wire down in it, leave a little bit of up on top, parafilm it on. Once you've got all the agar down, kind of sealing the bottom. Once all of this part's set up in your tube, now you can go to the rest of this, and the rest of this is pretty easy. You're going to have a copper wire that you basically just kind of hang through, and you can actually kind of bend the top of it over kind of like a right angle, so it'll actually just hang there nicely. And just make sure your copper wire and your glass tube are down in your copper solution for your different parts of the experiment, because it's this solution down here that'll change for your two parts of the experiment. But you'll basically add your copper sulfate solution here for part 1. Then you're going to go ahead and basically just use your LabQuest with your basically your alligator clips to measure the voltage. You'll measure the voltage, and you'll just switch out the solution in the cylinder for part 2 and make another measurement, and that's it. So the measurements happen really, really fast. They go really quickly. But the experimental setup, particularly getting everything here, especially with the agar, is where kind of most of the time for the experiment itself will pretty much be taking place. Now, in general, a couple things on the procedure. I've already pointed out these first couple. You really want that cotton ball as small as possible in the bottom of that tube. And you want the agar to come up above the cotton ball. And you also really don't want any air bubbles to be there as well. Air bubbles can also kind of cause some problems, unfortunately, for some of the conductivity that we want to be able to see kind of between our parts really of our galvanic cell. The other thing I will note here procedurally, when you go to get your wires, you are going to want to clean them. And we do clean them with acid, so you do want to make sure you're kind of taking caution. We are going to be using concentrated nitric acid. It's probably the most dangerous chemical you'll really use all semester long, so do be careful with it. If you get it on yourself, it will burn. It'll probably turn your skin yellow if it happens. But you only have to really dip the tip of your wire in that. And so you're just going to kind of dip the tip of your copper wire down in there, the part that's going to be ideally in your solution, put in the nitric acid for a few seconds, kind of swirl around just a little bit. And what you should see is the copper wire getting hopefully nice and shiny. That nitric acid will hopefully kind of oxidize any kind of outer coating off of that copper wire that might not be pure copper. And then the silver wire, you're going to prep it by dipping it in a little bit of an HCl, nitric acid, and water mix. This is also still pretty concentrated acid, so also still need to be careful with this also. And what you should see happen to the silver wires, it should actually get darker, almost kind of a blackish coating to it. Because what's really going to happen is this chloride here from the HCl is actually going to coordinate to the silver, and you're actually going to form kind of a silver chloride coating on your silver wire. And so those are kind of the prepping parts that you will do for the wires. Otherwise, everything else setup-wise is pretty much shown on that previous slide. Once you have your setup ready to go, you're going to be making 2 measurements. Part 1, you're going to use a copper sulfate solution. You're going to measure your cell potential. And ideally, the cell potential you measure, hopefully somewhere in a ballpark of about 0.10 volts or so. Might be a little less, might be a little more. But that's kind of give you a nice rough ballpark of what you probably should expect to see. And you're going to use that then with the Nernst equation to actually find E cell naught for copper 2+. That's going to be kind of the end goal of that part of the experiment. Part 2 of the experiment, you're going to be using the copper sulfide solution, and you're again going to use the Nernst equation, only this time you're going to use the Nernst equation to solve for Q out of that Nernst equation, which will help you find the copper plus concentration once you know Q. Then you can use the copper plus concentration to eventually find KSP for that copper sulfide. That's the goal of part 2. And again, the measurements here that you'll be making for both of these parts, once you have the setup done, will be really fast. But once you have the setup done and kind of make your measurements, it will take a little bit to go through some of these calculations. But I think the actual lab kind of manual does a pretty good job of walking you through step by step on a lot of those calculations. Waste-wise, all the waste for this stuff, these 2 solutions, will be collected. So do expect to see a waste container that's going to be picking up the waste of those solutions. Otherwise, safety-wise, the big things just are the acids, and that's pretty much it for this week's lab. It's a pretty short experiment. Usually doesn't take much more than an hour to an hour and a half. It's really just dependent on how fast or how quickly you kind of get your cell set up, because getting the agar portion of kind of that cell setup is the part that takes a while. And once you have that done, then the rest goes pretty quickly usually. And that pretty much wraps up this lab and actually wraps up our semester. Hope everyone has had a good semester, and we will see you all later.